In this video, we will look at how to write electron configurations and how to interpret electron configurations. So the electron configuration is the address, basically the address of every electron in the atom. And they look like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. This is the electron configuration for potassium. The coefficients, the 1, the 2s, the 3s, so the big numbers, those are the coefficients. That represents the energy level. The letters represent the shape of the orbital. So the S's, that's a type of orbital. The P's, that's a different type of orbital. And the exponents represent how many electrons are in that particular orbital at that energy level. So the 1s orbital has 2 electrons. The 2s orbital has 2 electrons. The p6 has a total of, or the 2p, sorry, has a total of 6. The 3s has a total of 2. The 3p has a total of 6. The 4s has a total of 1. And this is a more accurate way to describe the atom, more accurate than the Bohr model, because Bohr models are two-dimensional and electrons do not orbit the nucleus like planets orbit the sun. It's more complex than that. So the Bohr model is wrong, because your electrons orbit three-dimensional space. And so what happens is they just would occupy a general space. So s orbitals are spherical, and so the electrons in the s orbital, they just occupy a spherical three-dimensional space. P orbitals are dumbbell shaped, and those electrons would just occupy that dumbbell shaped space. D orbitals are more complex, and if you can imagine the orbitals stacked on top of each other. So if you look down here in the middle, you have the nucleus, but then you have also right here, you see the 1s, and you see 2s is right here, and then the 3s is on top of that, so they're stacked. And then within the second energy level, there are p-shaped orbitals. So just imagine your 1s orbital is spherical, which means that 2 electrons occupy that spherical space. Then on top of that, you have the 2s with 2 more electrons occupying that spherical space. On the same energy level, the 2 energy level, you have p-shaped orbitals. There are 3 of these p-shaped orbitals that have 2 electrons each, and those electrons occupy that three-dimensional space. 2 of them per p orbital. And so see how they just keep stacking. Then you have the next energy level with more electrons, and each of those orbitals can hold up to 2. Now there are 3 p orbitals, so the p orbitals combined can hold up to 6. Another way to say the same thing is with the orbital diagram. Instead of having exponents for the electrons, we have arrows, one up, one down. That indicates the direction of the spin of the electron. So for example, 1s2, that means there are 2 electrons in the 1s orbital. We have 2 arrows. 2s2, 2 arrows because there's 2 electrons. 2p6, there are a total of 6 electrons because a total of 6 arrows because there's 6 electrons. This periodic table, you need to write this down, copy this table, because this will help you write electron configurations. So we have blocks. This is what's known as the S block. We have the P block, the D block, and the F block. This is a guide, so notice how you can transpose that on top of a periodic table. So if we were to write the electron configuration for potassium, we know that potassium is in the 4s block and it occupies the first spot. We also know that we have to fill every energy level that comes before that. So the 1s will be full, the 2s will be full, the 2p will be full, 3s is full, and then the 3p is full. So we just start with the lowest energy level first. That would be the 1s. So we have 2 spots, right? So 1s, 2. Then we go to the 2s. We have 2 spots, 1, 2, so 2s, 2. We have the 2p block, right? We have 1, 2, 3, 4, 5, 6. So 2p6. Then we have the 3s. There's only 2, so it's 3s2. Then we have the 3p. Again, we have 6. And then, of course, down here in the 4s, since we're in the first spot of the 4s, it's going to be 4s1 for the first spot. A couple things to remember: the off-bow principle. Electrons will fill the lowest energy levels before the highest energy levels. So this is the order that you would fill your energy levels. It just follows the periodic table. You have the Pauli exclusion principle, which states that each orbital can hold a maximum of 2 and they have opposite spin. So if you wrote the orbital diagram, it would have to look like this. Instead of having 2 in this energy level facing the same direction, you need to have 1 up, 1 down. Then you have the Hund's rule. Electrons must occupy each orbital before a second can be added. So it's like this. We have to put 1 in each of these p's before we can double up in any of those p's. There's a shortcut that we will not be using, but I need to at least acknowledge it. It's called the noble gas configuration. Instead of writing out the full configuration for an atom, you can in brackets write the symbol for the noble gas that comes before it. In the case of sodium, sodium is right here, number 11. Neon is the noble gas that comes before it. Neon's configuration is 1s2, 2s2, 2p6. So instead of writing 1s2, 2s2, 2p6, 3s1 for sodium, we would just write Ne in brackets.